Welcome to another information program from CSI. Using excerpts from CSI's video series on vibration analysis, this program provides introductory material for those who are new to the measurement and analysis of vibration. Part 1 demonstrates how electronic instrumentation converts vibration into data the analyst can use for fault analysis and troubleshooting. Part 2 addresses issues vital to the acquisition of reliable data. Welcome to the fascinating field of vibration analysis.
It's far more efficient than preventive maintenance. It's far less destructive than running to failure. It's able to perform unbelievable equations in a single moment. With capability rivaling Superman's X-ray vision, it peers into plant machinery and assesses specific mechanical and electrical faults quickly and accurately. Is it magic? Not at all. It is vibration analysis. Some personnel have formed unfair or inaccurate opinions about vibration analysis, considering it to be some mystical black box magic. Welcome to CSI Training. This program unveils the black box mystery and demonstrates the value and simplicity of vibration analysis. Whether you are directly involved in a vibration program or just have an interest in the subject, we are sure you will benefit from the information and concepts presented here. Vibration analysis is a real benefit to industry today because of the ability to see what is happening inside a machine without interrupting its process in any way. Among the many mechanical and electrical problems that vibration analysis can determine are unbalance, misalignment, bent shaft, rolling element bearing defects, bearing looseness, loose bearing mounting, structural looseness, resonance, gear wear, gear misalignment, cracked or broken gear teeth, belt wear and looseness, chain wear and looseness, sheave runout, cavitation, fluid and airflow problems, sleeve bearing wear and looseness, oil whirl and oil whip, tilt pad bearing wear, and most electrical problems. Simply put, vibration analysis can be utilized to determine the source of just about anything that can cause machinery or production downtime. In order to successfully use vibration analysis to predict a machine's condition, we must have a basic understanding of how the vibration data represents the occurrences within the machine, and of course the terminology associated with vibration analysis. Vibration not only affects industry, but we are aware of it in our daily lives as well. For example, as you drive your car, you tend to notice any abnormal vibration and may purpose to have the tires balanced to see if that corrects the vibration. Let's take a look at an unbalanced car tire as it rolls along the highway. Assume this tire has an unbalanced weight or heavy spot at this location on the tire. As the tire rolls along the road, we will trace the path of the unbalanced weight. As the tire rolls 1/4 turn, the trace moves from the top position to a point in line with the center of the tire. The trace of the path has moved to the right because the tire is moving along the roadway over time. As the tire rolls another 1/4 turn, the trace moves further down and to the right. Again, it is to the right because this occurs later in time. The trace of the unbalance has now moved up to the center line of the tire, but is still to the right. The tire completes one revolution so that the unbalanced weight is at the top. This then is the trace of the path the unbalanced weight makes during one full rotation of the tire. As the tire continues rolling down the road, the trace repeats the pattern for each revolution or cycle. The horizontal or x-axis shows the time it takes to complete one cycle or revolution. The y-axis shows the amplitude or how much the unbalance moves during each rotation. Although we've been referring to this path of the unbalance as a trace, the technical term for it is a waveform. It is made up of the individual sine waves of the vibration of the machine, or in this case, the tire's unbalance. The analyst uses the waveform to indicate certain characteristics about a machine's condition. The analyst can view the same data from another perspective to gain additional information about the machine. If we view this waveform from the end, it becomes a single line. The technical term for this view of the data is a spectrum. The y-axis here is amplitude, just as in the waveform. The amplitude for the spectrum is dictated by the amplitude of the waveform. The x-axis is frequency, which tells us how often something occurs. This is done mathematically by computing the time for one cycle in the waveform. On the waveform generated from the unbalanced tire, we can measure the time it took to complete one revolution, since the x-axis is time. In this case, it is measured in seconds. One cycle or revolution of the tire took 0.05 seconds. To obtain the frequency, we simply get the inverse, which is accomplished by dividing this time period, 0.05, into 1. This yields 20, which means that this unbalanced sine wave occurs 20 times a second. Multiplying this by 60 seconds gives us the number of cycles that occur in 1 minute. In this case, we see that it is 1200. In other words, the unbalanced sine wave repeats itself 1200 times per minute, which is 1200 cycles per minute, or 1200 CPM. Of these expressions, CPM is the most common in the field of vibration. On the spectrum, we can label this frequency axis as CPM, and the peak would be at 1200 CPM. Recall that after we determined the time for one cycle of the sine wave, we divided the time into 1 to obtain the inverse, which in this case yielded 20. This means that the sine wave repeats itself 20 times a second, which can be said as 20 cycles per second. This same peak in the spectrum can be referred to in terms of cycles per second, or CPS. It can be said then that this peak represents energy that is occurring 1200 times per minute, or 20 times a second. The technical term for cycles per second is Hertz, which is commonly noted as Hz. Hertz is simply a measurement of how frequently the cycle occurs per second. These two frequency units, cycles per minute and cycles per second, indicate the precise occurrence of energy, but the analyst often compares these frequencies to the turning speed of the shaft to pinpoint the source of the energy. As we were tracing the unbalance on the tire, we noticed that the unbalance created a sine wave that started and finished at the same time the tire did. In other words, the unbalanced sine wave completed one cycle every time the tire completed one rotation. In this example, the cycle for the sine wave is compared to the cycle or speed of the tire rotation. To express this spectral peak in terms of the speed of this tire, we can say that this peak represents energy that occurs one time every time the shaft turns once. This peak is commonly called a 1 times shaft turning speed peak. The unit used to measure frequency as a multiple of shaft turning speed is orders. In other words, this is a peak at 1 order of shaft turning speed. The frequency units are displayed in CPM, which is the number of occurrences per minute, Hertz, which is the number of occurrences per second, and orders, which is directly related to the turning speed of the shaft at the measurement point. There are times when one of these units may be more helpful than the others in looking for a particular fault. Other times another unit may be more helpful. Use them to maximize your analysis capabilities. We have used the unbalance of an automobile tire in the waveform and spectral data examples. Because we are really interested in industrial machinery and equipment, let's see how this applies. The same waveform and spectral data could be generated from industrial machinery that has an unbalanced problem. If the machine has other sources of vibration, they too would show up in waveform and spectral data. If this machine has a problem in addition to unbalance that creates a signal 2 times every time the shaft turns once, the energy from this signal will be added to the waveform. This new energy will create 2 complete sine waves during the time the unbalanced sine wave is created. Measuring the time it takes to complete one cycle, we see that it is 0.025 seconds. In other words, this cycle occurs twice as often as the unbalanced cycle. The analyzer processes this waveform signal and actually separates the waveform into 2 individual sine waves. The calculations are performed for each sine wave, which has the net effect of viewing the discrete sine waves from the end, which is the spectrum. The frequency of this new peak can be expressed in each of the 3 frequency units and can be said to show energy that occurs 2,400 times per minute, 40 times per second, or 2 times during each shaft rotation. This 2 times peak is often called a 2-order peak. Here we can see how each of these peaks were generated because of specific mechanical properties. It is important to understand that there is a mechanical or electrical occurrence represented by every peak in the spectrum. The source of the mechanical vibration could be flow, electrical, or some other force, but the effect we measure is mechanical vibration. If this data was from a pump, a peak could show up which would equal the number of vanes on the impeller. The waveform here is more complex because of the added energy. Now during one rotation of the shaft, 7 complete cycles are generated. Again, the processing separates the waveform into individual sine waves. The calculations are made which convert this data into a spectrum. This new peak represents energy that occurs 7 times during each shaft rotation, 8,400 times per minute, or 140 times per second. It is common for machinery to generate many frequencies that create a very complex waveform, and thus many peaks in the spectrum. Determining the source of the peaks and the severity of the problem is the challenge for the analyst.
Now that we have seen how time waveforms and frequency spectra relate directly to physical events, it is important to know the proper use of vibration sensors for measuring that data. By following the techniques in this program, you will be able to acquire quality vibration data and avoid many common errors.
Other questions include, which is the best sensor to use? And where are the best data points on pumps, motors, gearboxes, belt-driven equipment, and pillow block bearings? All of these questions and more will be answered. The previous program, Introduction to Vibration Analysis, showed how the spectral and waveform data we acquire is a representation of energy actually occurring within the machine. This program builds on the previous program and shows how to get the best data that is an accurate representation of the energy actually occurring in the machine. By applying the information presented in this program, you will be able to acquire the best possible data that will aid in the machinery analysis. To maximize the benefit of collecting this data, especially trending, certain conditions must be met. The data must be collected at the same locations, in the same way, using the same sensor type and the same sensor mounting. The general rule of thumb is, acquire 2 radial readings per bearing location and at least 1 axial per shaft. The radial reading should typically be the horizontal direction and the vertical direction. These radial readings will give the analyst an idea of how the machine is moving up and down as well as side to side. For horizontal machinery such as this, where the mounting is at the bottom, we typically would expect less movement up and down because it is limited by the mounting. The analyst compares these vertical readings to the horizontal readings to check for problems, such as a soft foot condition or loose mounts. An axial reading is one which is the same direction as the shaft or axis. In this motor, the axial measurement could be made at either end. We use the axial measurement to indicate how much the shaft is moving from end to end. Theoretically, the readings at one end should be the same as the other, since the same shaft extends the length of the motor. Actually, the readings will vary some from end to end, due to possible differences in mounting positions and the physical design of the machine. So in order to get the most useful data for trending and routine analysis for each machinery component, collect a horizontal and vertical reading at each bearing location and at least 1 axial reading per shaft. Some suggestions should be made regarding the location of collection data points. A previous section identified the need for horizontal and vertical measurement at each bearing location, as well as at least 1 axial measurement per shaft. The magnet with 2 poles can be used on a wide variety of surfaces. If the machine has a smooth area, such as this one has, the magnet mount can be placed directly on it. The outboard end of this motor poses a special problem. The only smooth area is on this fan cover. Using its surface for mounting does not give an accurate picture of the motor vibration, but simply the energy of the cover, which may be transmitting only a very small portion of the actual machine vibration through it. With the cover removed, we can get a better idea of what we are trying to achieve. This is the fan, and the bearing we need to monitor is further inboard, here. The best reading could be achieved by removing the fan cover and placing the sensor on the casting near the bearing. Obviously, this is not an option, since the cover must be in place while the data is acquired. The alternative is to collect data through this area of the motor. With these cooling fins spaced closely together, it becomes necessary to place the magnet mount on the fins. It could be placed across the fins or in line with them if the magnet's two poles will line up. Although the horizontal measurement could be made on either side and provide good information, it is best to maintain the same horizontal measurement orientation from one routine survey to the next. The analysis equipment is so precise that even minute differences from one side to the other can significantly alter the data. The best place for an axial measurement is near the shaft center and on the bearing in the load zone. The load zone is the radial direction the most force is applied during normal operation. In horizontal machines, this is usually in a clock face position of 4 to 5 o'clock or 7 to 8 o'clock, depending on the direction of rotation. The axial measurement on this motor could be made at any of several places. The simplest place is on the end bell at the recommended clock face position, but the same restrictions apply for this axial measurement as for the radial measurements. Don't make measurements on the end bell, as it will only be an accurate indication of the bell's movement, not the machine's movement. If no better place is available, the axial reading could be made on a through bolt that fastens the end bell to a solid part of the motor. Be sure the bolt is tight. Long bolts may have resonant frequencies that substantially reduce the linear response range of the sensor. Another usable location is the lift hook. If the lift hook is simply a loop, be sure to make the measurement at the base of the hook. If the lift hook is an integral part of the housing and of substantial size, it could be used and still obtain reliable data. Be sure the sensor is pointed in the true axial direction. The motor foot provides another location for the axial reading. If it is used for the axial measurement, the analyst needs to keep this in mind when analyzing the data. Because the foot is firmly fastened, any axial movement will be minimal. An axial reading on the lift hook would have more freedom to move and thus would have much higher levels of energy. When comparing amplitudes for radial versus axial readings, keep this in mind. Never use the electrical junction box for an axial measurement, even when it is a heavy casting of the motor housing. Data taken here will have higher levels of electrically related frequencies that may indicate motor problems that don't really exist. On the pump, the horizontal measurements should be made on this flange because the bearing is mounted directly in line here. Be sure the sensor does not cross the joint, which may cause it to rock and generate erroneous frequencies. The center section of these pumps is hollow, and measurements should not be made here, as the signals will not be accurate. The outboard bearing is located in this area, and the horizontal readings should be made here. Axial measurements could be made at either end of the pump, but the impeller end tends to show energy due to flow, which can mask other problems. The same criteria apply to vertical mounted pumps and motors. 2 radial readings at each bearing location and at least 1 axial reading per shaft. The radial readings should still be 90 degrees apart, but should be called X and Y direction. Machines that use pillow block bearings require another measurement to accurately diagnose certain problems. There should still be 2 radial measurements per bearing, but an additional axial measurement should be made on each bearing. Since the pillow blocks are independently mounted, it is common for them to be cocked on the shaft. The axial measurement is a good indicator of this problem, as well as early bearing wear due to heavy axial thrust. Pillow block bearings on shafts like this may be inaccessible due to guards, covers, or simply be out of safe reach. If the guard is mesh, the long stinger may be used to reach through it for the radial measurements. Although the stinger or long probe does not provide the best data, it is still far better than no data. However, it is important to collect an axial measurement on each pillow block bearing, and the guards or covers often prevent that. A better way to measure the covered pillow block bearings is to install a hatch door so that a magnet mount sensor can be used. The linear frequency range will be increased substantially to be sure to catch bearing degradation. Oftentimes, the pillow block bearing has rounded surfaces that cause the magnet-mounted sensors to rock. In cases like this, it is better to install a mounting pad for the sensor. The best way to measure guarded pillow block bearings is to install permanent sensors at the measurement locations. These sensors are then wired into a panel that has terminals for BNC cable connections. The measurements can be made without compromising safety or data quality. Remember that in most instances, the analyzer will be providing power to these sensors and that the sensor receives an electrical shock and requires a 3 to 5 second settling time. Belt-driven equipment has special considerations for selecting the measurement locations. Although the common rule of 2 radial readings and 1 axial per shaft still applies, it is the orientation of the radial readings that varies depending on machine design. When the center lines of the motor and driven equipment are in the same horizontal plane, there is no change in the measurement locations. When the shaft center lines are not in the same horizontal plane, 1 radial measurement should be made in line with the centers of both shafts, and the other should be 90 degrees to it. This inline measurement is also the direction of belt tension and is used to indicate eccentricity or excessive runout in the sheave as well as a bent shaft. The perpendicular or 90-degree measurement better determines sheave misalignment and belt resonance. It is important to acquire good axial measurements to confirm misaligned or bent sheaves. The same recommendations should be followed for these axial measurements as axial measurements on any other machine. Although the next video program in this series discusses gearboxes in depth, here we will cover the best measurement locations for them. Gearboxes have high-frequency occurrences that require exceptional data collection for proper analysis. Routine surveys for single reduction parallel shaft gearboxes require a minimum of 1 radial and 1 axial measurement at each bearing location. Use 2 radial measurements when troubleshooting problems in a gearbox. The extremely high frequencies associated with gearboxes may necessitate 2 measurements being made for each sensor location. 1 measurement would be low frequency, high resolution for detection of balance, looseness, misalignment, and bearing problems. The other reading would be very high frequency to 3 or more times the gear mesh frequency with high resolution for determining gear condition. The direction of radial measurements should be in the line of force of the gears, through the center line of the shafts. As in other measurements, we need to be as close as possible to the source of the energy with a solid transmission path through a web or internal frame to the measurement location, and as close as possible to the bearings actually supporting the gears. For multiple reduction and angle gearboxes, 2 radial measurements should be made at each bearing location as well as the axial measurement. This second radial measurement should be perpendicular to the first measurement. In order to get the best data, we need to understand some facts and limitations of the various sensors. Each of these sensors or transducers has distinctive characteristics that may make it more desirable than another for a specific application. All of these transducers are either piezoelectric velocity transducers or accelerometers. Their size, sensitivity, and linear frequency range are the primary differences. Here, we will focus on accelerometers. Inside these accelerometers is a piezoelectric crystal. This means the crystal is under pressure, and when an electric current is applied, the output voltage changes with a change in pressure. The change in pressure is produced by the vibration of a machine impacting the sensor. The analyzer reads this voltage output and stores it as your data. Because of the orientation of the piezoelectric crystal in the sensor, it is very directional. Typically, 95% of all the energy the sensor picks up is directly in line with the sensor. Only 5% of the vibration data is from a lateral direction. Because the transducer's sensitivity is very directional, it is important to get the data that will be of most benefit. In this machine, as well as most machines, we are interested in the energy generated by the rotating shaft. The rotating shaft transmits the energy due to misalignment, unbalance, bearing failures, and other faults to the casing. The sensor should be pointed directly to the center line of the shaft in order to pick up the most information from rotational energy. In order for the energy to get from the shaft to the sensor, there must be a good solid path to the sensor. The cover on the inboard end of this motor has reinforcing vanes molded into the casting. These will transmit energy from the bearing location to the sensor with little loss. However, the places without the reinforcing vanes are voids, and the energy is not transmitted as well to these locations.